Bismillah ar-Rahman ar-Rahim. This illustration is made under supervision of Professor Dr. Nihal Fayez Arid, Head of Communication and Information Engineering Program Department at the Faculty of Engineering, Mansoura University. Today we are going to discuss one of the most common electromagnetic devices, which is parallel plate capacitor. This is Sharif Aouni, a mechatronic science engineering student at the Faculty of Engineering, Mansoura University. Let's begin by knowing what is exactly the capacitor is. A capacitor is a device that stores electrical energy in an electric field between two metal sheets or two conducting sheets separated by a distance and having a dielectric between them. In this illustration, we are going to discuss the major factors affecting capacitance, electrical field, and stored energy in the capacitor. So let's begin with the capacitance formula. The capacitance could be calculated by multiplying the permittivity of the air times the permittivity of the medium, or the medium constant, the dielectric constant, times the area of the plates divided by the distance between the two plates. As you can see from the formula, the capacitance is directly proportional to the area and inversely proportional to the distance between the two plates. Let's have a look on this simple capacitor, which consists of two plates separated by a distance and having a dielectric material between them. The dielectric material could be a custom-made material, Teflon, paper, glass, mica, or even ceramic. In this example, we have a simple capacitor which have a plate area of 100 squared millimeters with a separation gap of 10 millimeters. Let's see what will happen to the capacitance if we change the plate area or the separation gap. For example, with this construction, we have a capacitance of 0.89 times 10 to the power minus 13 farad. Let's see what will happen to the capacitance if we increase the area of the plate. So the capacitance is increasing proportionally to the area. Let's see what will happen to the capacitance if we decrease the separation gap between the two plates. Therefore, the capacitance is increasing. In the previous example, the separation gap was filled with air. Let's look what will happen if we try to change the dielectric material. For example, a paper material. When we insert the material between the two plates, the capacitance is increasing. Let's try to change the permittivity constant. The dielectric constant is 5 for now. Let's see what will happen if we decrease the constant. Therefore, the capacitance is decreasing. For a given capacitance, let's see what will happen to the accumulated charges on each plate. When we have 0 volts from the battery, we don't have any charge on any plate. Let's see what will happen if we increase the voltage. Charges are forming on each plate, and it is directly proportional to the voltage from the battery. As I mentioned before, the capacitor is an electromagnetic device which are being used to store electrical energy. The stored electrical energy can be calculated with these formulas. the stored energy equals half the amount of charge times the voltage across the plates, or the stored energy equals half the capacitance times the voltage squared across the capacitor. Let's go back to the simulation and see what will happen if we change the parameters affecting the stored energy. When we increase the voltage, the stored energy will be increased, and when we decrease the voltage, the stored energy will decrease. Let's have a look on the capacitance effect on the stored energy. If we increase the capacitance by decreasing the gap between the two plates, the stored energy is therefore increasing. Finally, let's do the simulation for the previous example, and let's see what will happen to the capacitance, plate charge, stored energy, and the voltage across the plates, and the electric field between the two plates. So let's set our probes, the negative to the negative and the positive to the positive. When we have 0 volts, we don't have any plate charge here, and we don't have any stored energy. Let's see what will happen to the electric field lines, and we have an electric field tester. This probe, I will put it between the two plates. When we apply voltage to the plates, see what will happen. We have electric field is forming between the two plates. When we increase the voltage, the electric field therefore is increasing, and it's reading 63 volts per meter. When we increase the voltage more, the electric field is increasing proportionally to the voltage across the battery. Let's see what will happen if we reverse the polarity of the battery. So the electric field is also reversed, and the electric field lines is reversed from the two plates. In the previous example, we were studying a capacitor with only air gap. Let's see what will happen to the parameters if we start using a dielectric material. In this case, we are not applying any voltage to the plates, so we don't have any charge on the plates, and we don't have any stored energy. When we increase the voltage across the plates, electric field lines are forming, plate charges are forming, and we have a stored energy in the capacitor. Let's see what will happen to the stored energy when we insert a material. For example, I will choose Teflon. When we insert the material in the capacitor, as you can see, the plate charge is increasing and the stored energy is increasing. Let's try to change the dielectric material, for example, to glass, which having 4.7 permittivity dielectric constant. Let's see what will happen to the electric field with the same voltage. It's increasing, and the stored energy is increasing.